Okay, this is probably going to be a little bit of a short lecture today because I want to give you time to work on the lab, but I do want to talk about it just a little bit. So let's go ahead and get started. So first thing is, you might remember from Baudot's 5-unit code, and this is review, that basically it took the symbols we wanted to send, it made them into these bit patterns of ones and zeros or highs and lows in a sequence. And then the way that Baudot's system worked is you had these rotary mechanical things that would then rotate around and then connect each bit on the line for one time period, sending all 5 bits across. And then this had to be synchronized with that. So there was the addition with that having to be synchronized of an additional bit that was the start bit. And that was the solution to making sure those were synchronized. In other words, they would be stopped until the start bit came along. It would then turn on, leave the start bit on the line for one period, and then click through each of the other 5 bits. So a review for the start bit, if we were to look at the line, it would look something like this. We have the start bit, and then the 5 data bits, and then the stop bit, which it has to be opposite of the start bit. And then we go back to the line being idle after that, which could be dropping low again and having another start bit and another message. But the falling edge of this would engage the motors on each end. They would then click through the start bit period, all of the other period, stop bit period, and then go back to being disengaged and waiting for the next start bit again. The stop bit, the reason for that was to force the line back to the idle state and make sure it's in that idle state long enough for the machine to be reset, ready for the next serial data unit to be sent. So the concept of that serial data unit can be extended to more than 5 bits, as in Baudot's time. So we could do 8 bits to send an entire byte. And that would be the same kind of concept, except here. Now, one thing to notice here is I have bit 7 first and bit 0 last, where back here we had bit 0 first and bit 4 last. It's really up to how we design the system to send that. So it could be the most significant bit first, or it could be the least significant bit first. And we're going to talk about that later on because that's going to be important for you in this lab. So the only limitation here is that the clocks have to be synchronized from here through there, and then that's it. So they just have to be pretty close, not 100% exactly, perfectly the same, synchronized over long spans of time. Okay, a serial data unit, our definition for that was start bit, stop bit, data bits in between them. That whole thing as one unit of serial data that's getting sent on the line. If the line idles high, start bit has to be low, which makes the stop bit the same as idle, has to be the same as idle. Now, we could have more or less data bits. We could have more than one stop bit. We could also have parity. We'll talk about that later in the semester for error detection. But the concept is pretty straightforward for what we're going to be doing in the lab. We're going to be implementing this in the lab. And as we said, modern systems have special hardware that does the transfer and the receive for us. Those are usually called UARTs, which stands for Universal Asynchronous Receiver Transmitter. So it has both a receiver in it, has a transmitter in it. It's asynchronous, meaning it has a start bit that starts the thing, has a stop bit that is used to return the line back to idle. And universal, the universal part of that just means usually the rate is programmable in the data format. How many data bits do we have? How many stop bits do we have? It's usually programmable in some way. We'll talk about more on UARTs, more about UARTs later on. But there's another way to implement this. It's implemented in software with code. That's what we're going to do for the lab. And that type of implementation is called bit banging, or a bit banged serial transfer. So this has more on bit banging in a later lecture lab. That's actually going to be today. Okay, so today, implement bit banged serial transfer. So in today's lab, we're going to wire up 2 systems, a transmitter and a receiver, just like you did for lab 2. Except rather than just putting data onto a channel and getting it to read the data off the channel, like whether it's high or low, today we're going to send an entire byte across that channel using this serial data transfer of a serial data unit. So you're going to write a sender program that will send a byte by sending a start bit, meaning pull the line low, and then after leave it low for one time period. So pull it low, delay for one time period, and then go through all 8 bits of the byte, sending them one at a time. Put a bit on the line, delay, next bit, delay, next bit, delay, next bit, delay, and so forth, all the way through the entire byte. And then when we're done, set the line back high, opposite of start bit, delay for 1 unit, and then we're done with that byte. Get the next byte, pull it low, send the data bits, put it back high, wait, and then send the next one. So we're going to repeat that for every character that we want to send. The next thing down here is on the other end. To receive that, we're going to have to write the receiver program that sits and waits for the start bit. In other words, it waits for the line to go low. As soon as the line goes low, it times off, reads the line, waits, reads the line, waits, reads the line, waits. Does that for all 8 bits. After it's done with doing that for all 8 bits, it has a byte. Print out the byte. We'll read the state of the stop bit, print out the byte, and then we're done with that when we go back to waiting for the next start bit. So notice that, like we said earlier, there are 2 options for sending the 8 bits. There's 2 options for the order that we would use to send those. And those 2 options are basically the start bit always has to be first. So start bit, in other words, if the line is idling high, the start bit is always pulls it low, and that has to be there at the first bit. Now, the next thing, though, is the data bits sent one at a time. But there are several data bits there, and so we have a choice of which order do we go through. Do we start with the most significant bit and work our way down to the least? Or do we start with the least significant bit and work our way up to the most significant bit? And it turns out that most UARTs and most systems use this one. They start with the least significant bit. That goes on the line first, and then we work our way up to the most significant bit later. But we could make a system that works the other way as well. And there are systems that are set up like this. And it really doesn't matter because each bit is just taking its turn on the line one at a time. So generally, though, it'll be least significant bit, and then the next, and the next, and the next, all the way up to the most. Generally, this is what's used in UARTs. All right, so here's an illustration of those 2 orders going through. So the sender start bit is always in the first position. And if it's most significant bit first, then B7 will be the first thing that goes on the line. So this is time progressing this way. So as we go across time, we would see the start bit would pull the line low, and then we would have bit 7, and then bit 6, and bit 5, and so on all the way down to bit 0, and then after that, the stop bit, assuming there's no parity bit in between that stop bit. Now, least significant bit first will go the opposite direction. B0, and then 1, and 2, and 3, and 4, 5, 6, 7, and then stop. Now, again, like I said, the one that tends to be used more is the second one here. This tends to be what you see in most UART-based systems. Least significant bit goes out first, and it works its way up to most, and then it's done. That's probably what we should use for the lab. Now, you'll notice that I have these arrows that I added here, these green arrows along the top. That's the sender putting the data on the line, and you'll notice that regular interval here. Puts the start bit on. 1 unit later, puts bit 7 on. Or let's do least significance, that's more common. Put the start bit on. 1 unit later, B0 goes on the line. 1 unit later, B1. So in other words, pull the line low, wait for 1 unit. Put bit 0 on the line, wait for 1 unit. Put bit 1 on the line, wait for 1 unit. Put bit 2 on the line. And you notice these little X shapes here, that's the line changing from one to the next as we're taking 1 bit off and putting the next one on. It can't instantly change state. So we've got this little X showing that it takes a little bit of time for the voltage level to change from high to low, back to high again as we're going across the signal. And then when we get to the end, pull the line back high, and then we wait for 1 unit, and then we're back to idle again over here, waiting for to send the next one. Now on the receiving side, you notice that we're sampling the line, but you'll notice that we're sampling it. We see the line go low here, but we don't sample it exactly 1 unit later. We're a little bit past that. But then after that first one, now we're on that same regular time interval that we had up here, but you'll notice it's slightly offset from where we're putting the data on the line. We're going to talk about that here for just a second, because that's going to be important for your success in this lab. So you'll note in looking at that diagram, this is the same diagram from earlier with the least significant bit first. You'll notice that the sender puts a bit on the line, and then delays. And that delay will always be the same time period for every one of these units, including the start bit period and actually including the stop bit period. It'll keep it on the line for the same amount of time before we're back to just idle. But on the receiver, you'll notice that there's a longer delay from the start bit to the other bits when sampling the line. So all these are the same as those, except for this one. So the question is, why is that? Why do we have that longer period here? And the answer is pretty simple. You can pause it here and kind of think about why you'd want to sample it here rather than back there at the exact same spot as it was being put on the line. So maybe pause the video, think about that, see if you can come up with the answer. And then I'll give you a couple seconds here, and then I'll tell you what the reason for that is. That's going to be important for your lab. So take a couple seconds here. Okay, so let's answer that question. The question was, why is this sample period here, this time delay here, from when we see the start bit line go low to when we sample the line for bit 0 longer than all of the rest of them? And the answer for that, or to that, is that, well, imagine we did sample it right here. What is happening to the line at the point where we'd be sampling it if we saw it go low and we were we didn't have much of a delay for noticing that line go low? We'd be sampling it right here when it's changing. And so that means any difference in the clock speeds between the two, or even if there weren't any difference between the clock speeds, I'd be sampling while it's changing before it has settled into the bit value that's being put on the line. So in other words, we'd be looking at it while it's in transition. If we just sample it at one time while it's in transition, we might sample it and think, oh, it's the previous state hasn't had time to settle into the value yet. Or if the clocks were slightly different, that sampling period would drift off to be on the previous bit rather than the next one. So the general idea here is we want to sample it towards the middle of this bit period. So we want to have, rather than this be 1t, let's say this is t, is that time between there and there, we want this to be 1t would get us to where it's changing, and then another half would get us to the middle of that bit. So this would be like 1.5 times our sample period, or our bit period, and then after that it's 1, because then it's the same for each one. But we wouldn't want this to be exactly 1, because that would put us on the point in time where the signal is changing, and we want to be more towards the middle of it when it's stable. And when you write your code, you're probably going to want to implement your receiver to have that little bit of extra delay. And it might not be exactly 1.5 that gives you the best results. It might be like 1.25 or 1.3 or something like that. Because there is going to be a little bit of delay when this gets put on the line and then when our receiver notices it. So this will probably be a little bit after that anyway, but you still don't want to be anywhere near where that changing period is, because if your clocks are slightly mismatched, then the receiver can drift off and be getting the previous bit when it should be getting the one that we're on. Okay, now how are you going to write your code for the lab? A quick review for that is bitwise operators, meaning that you're going to have to manipulate bits. In other words, how are you going to get each bit from a byte one at a time? And you should have learned this, at least this should be familiar to you from systems programming. Everybody in here should have had the systems programming class. Should have completed that successfully. And one of the things that we cover in there is the kind of low-level bitwise operators that are available to us. And here is the set of them here. There's 6 bitwise operators here. Bitwise AND, bitwise OR, bitwise NOT, or XOR, bitwise NOT, and then shift right, shift left. And then each of those has a modifying assignment version of it as well. Bitwise AND equal. That should be OR equal there. Let me fix that. I don't know why that's plus equal. OR equal. XOR equal, not equal, shift right equal, shift left equal. And you should remember those from systems programming. If you don't, you should go back and review that. Maybe look at your lab where you converted characters into binary, printed them out one bit at a time. And these are going to be really useful for us now, because we need to send one bit and then go to the next bit and send the next bit and then go to the next bit, send the next one, and do that in a loop that repeats 8 times for all 8 bits of a byte. Now let me give you a quick overview of how to use these. I'm not going to give away the source code for how to do this. I want you to try to figure that out yourself. But one of the things is, first off, storing a byte. Since the Arduino is C and C++ based as the underlying language, these C bitwise operators are going to be useful to us. So the first thing is how to store a byte. Well, in C, that's an unsigned character. Unsigned char variable is 8 bits. It's an 8-bit byte, 8-bit variable. So this byte underscore value that I have here has 8 bits inside of that of storage. It's 1 byte worth of storage. Now, to isolate just the least significant bit, meaning if I have 8 bits and I want to get rid of them all, but leave the least significant one, the one in bit position 0, the ones place, then I can use this bitwise and it with 0, 1. Because if you remember what AND does, it gives an output of 1 if both of them are 1. It gives an output of 0 if one or the other is 0. In other words, the only way it gives an output of 1 is if both of them are 1. So by putting a 1 in this least significant place, if I have a 1 in the least significant bit place of the byte value, then that 1 will be passed through. If I have a 0 here, I'll get a 0 passed through, and all of the other bit positions that aren't 1, they'll all be forced to a 0 because that's how AND works. So this is a form of masking to get rid of all of the bits that we don't want and isolate just the 1 bit position we do want. So in other words, this will produce a 1 only when the least significant bit of this byte is a 1. It'll produce a 0 when there's a 0 there. So that's a way to isolate just the least significant bit. Now you might think, well, after we've isolated that, I could put an if statement around something like this and say if byte value and 1, that means that bit is 1, so we need to set the line high, else set the line low. So that's the kind of thing you're going to have inside of a for loop. Now, after we've sent that one on the line, we delay for 1 time unit, whatever our time unit is. And then after that, we have to now somehow go to the next bit in that byte value. So how do we go to the next one? So to move the bit pattern over 1 bit to the right, in other words, take the bit pattern, shift it over 1 space to the right, we need to do something like this. Byte value, shift right equal 1. That says move the bits in this thing 1 space over to the right, and then put it back into that value. So in other words, this is taking this variable, changing the contents of it, so we've shifted it over 1. And then the next time in the loop, now the least significant bit will be the one that was in 1 position over. And then we can use that same if statement that we had back here. If byte value and 1, then put out a 1, else output a 0. Or in other words, put out high, else put out low, and then go to the next one. And if we had that in a loop that went 8 times, we would go through each of the 8 bits one at a time. Now, on the other end, on the receive end, we need to OR a bit on, and the one that we're sending out in the least significant place, we're probably going to want to put in the most significant place and then shift it over 8 times. So we're going to, in other words, we're marching them out to the right and then marching them in to the left. And when we're done with all 8 of those marches, then we're going to have our value, same value we had on one and the other. But to put add a bit value, a bit onto a thing, we use, instead of and equal, we mask the bit on by doing this. And so here I'm saying byte value or equal 0x80, and 0x80 looks like this. So all 8 bits are low except for the most significant one over here. And that most significant one over here, that's forcing the one in that position on. And then we could say, have an if statement that says, hey, if the value that I read from the line was a 0, then leave it alone. If the value I read was a 1, then OR it with 80. And then after that, or before we get the next one, shift that whole thing over 1 and then put the next one on. Shift it over 1, put the next one on. So in other words, we're going to march them out of the transmitter one at a time from least significant to most. We're going to march them in from most, working our way to least. And after 8 times, we'll have the same value that we had on the sender now in the receiver. So do some thinking about that. And I'll give you a quick hint here for how to do that. I've already given you some hints, but you're going to have pull the line low for the start bit, delay for 1 unit, have a for loop that goes through 8 times, put the least significant bit on, shift over 1, least significant bit, shift over 1, least significant bit, shift over 1. And then after those 8 times we've done that, set the stop bit, put the stop bit value out on the line. In other words, set the line back high, and then wait 1 unit, and then go back to waiting for them to send the next thing. On the receiving end, you're going to have a loop that waits for the line to go low. When the line does go low, then what you're going to do is delay for 1 unit, but not just 1 unit, probably 1 unit and a little bit, 1.5 maybe, and then read the line or the bit on, shift over, or go back to the top of the loop, shift it over, or the next one on, shift it over, or the next one on, and so forth, till we get all 8 of them put on there. And then wait after the loop, wait 1 extra time unit, delay that 1 extra time unit, read the line for the stop bit. And after you've read that line for the stop bit, then go back to waiting for the line to go low again. So in other words, we're kind of emulating this thing here. So go back and look at this diagram as you're working on that for the sender, and then this diagram of timing for the receiver. Okay, so for Lab 3, you are implementing that sender and receiver. What I would do is hook up your Arduino boards, make sure your Lab 2 still works, make sure you can still send that the stuff from one end to the other end. And really, that's what you're doing for this. And then after you get Lab 2 working, you know the channel works, then write your code for Lab 3. If you're modifying Lab 2, make sure to do a save as, so you don't lose that, because that Lab 2 can be useful when something's not working to say, well, is the channel working? You can run your Lab 2 and see, put high, put low. Yeah, it's going across to the other end, so that's not the problem. So one other hint before we take a look at the lab sheet here is be careful with using the delay function. It can only delay for an integer number of milliseconds. In other words, the delay function delay has to be a whole number of milliseconds, and milliseconds are 1,000th of a second. Well, when you get up into the higher baud rates that we're going to do with this lab, you need a resolution of a timer that is finer grained than milliseconds. So think about, is there another function that we covered in here that can delay for a time unit that is something finer than milliseconds? And as a hint, maybe microseconds is a finer resolution. So if there were only a way to delay microseconds rather than delay for milliseconds. All right, so that should be a good hint for that. All right, so let's take a quick look at the lab sheet. So give me a second here to switch the display over. Okay, so here's what the lab sheet looks like. You're going to connect the 2 Arduino boards and use it to transfer. Now you can work with someone else, or you can work by yourself. If you have a roommate or somebody that is in your same social group, feel free to work with that person and submit this kind of as a group project with those people. Or you can do it by yourself because you have the 2 Arduinos, you have the wires to connect them. You can do it all yourself if you want to. But you're going to be using the Arduinos and writing 2 programs. One that goes on one Arduino, it's the transmitter. One that goes on the other one, that's the receiver. Now, the first thing is in the setup, you're going to be configuring the serial connection to the PC to run at 9600 BPS. Now, this rate here has nothing to do with the communication from Arduino to Arduino. This is just the rate at which your PC is going to talk over USB to the Arduino board. So when you go to make this run at higher rates, you don't have to ever change this for this lab. This is what it is. That's basically our way of talking to the board. Now you're going to configure a general purpose I/O pin to act as an output. I would suggest you use the same pin you used for Lab 2. That's our channel. You're also going to configure the LED GPIO pin to act as an output, so we're going to be able to see the light change as the message goes across the line. So in other words, when you send a message, you're going to see the LED go and flash on and off. It won't make that noise. That was my sound effect to make it seem exciting. But you're also going to set that output port pin and the LED pin in initial idle state of high. In other words, when you run this, you want it to idle high. So you're going to set it as an output. You're going to set it high to say, now we're in the idle state. And then in the loop part of this, you're going to read a key from the serial interface of the PC, and that's using serial .read to read that character. If there's a character available, read it. And then you're going to take that character, store it in a unsigned character variable, a byte variable, and then you're going to then send that 1 bit at a time using that method we talked about. So you send the start bit, you wait for 1 time period, send the data bits of the message in a for loop to go through all 8. In other words, send the least significant bit, wait 1 unit, send the next one, wait 1 unit. Do that for each of the bits. And then at the end of that, set the stop bit level, which is just going to be setting the line high. Wait for 1 time period. And in this case, it says start with a 10 bit per second baud rate. So that's going to be relatively slow compared to what we're going to do later on. Now, if you're having trouble with this, you could even set this to 1 bit per second or 1 bit every 2 seconds if you want to, by just increasing the delay that we're waiting here. And then you can watch it and see the actual LED turning on and off and make sure you're getting the right pattern in. But one of the things about that, starting with that 10 bit per second baud rate, notice that you have to change the time period anytime you change this. So what I would suggest doing is using like a pound define for that. In other words, pound define your delay, the number of milliseconds that would be. So calculate what that would be, pound define it, or make the compiler compute it for you. So with a 10 bit per second delay or baud rate, you're going to want your delay to be 100. If there's 1,000 milliseconds in a second and you want 10 bits per second, what should your delay be? Well, your delay is going to end up being 100, so a tenth of a second. Well, when you go to the later parts of the lab where it wants it to run faster, you're going to have to come up with a different number. And since there are a lot of places that's being used here, you're going to have to pound define that and then recompile it each time to get the rate to change. So that's program 1. You would type A in the serial console, hit enter, it'll send the letter A, 1 bit at a time to the other end. Now on the receiving side, it's the same thing, but in reverse like we talked about. In other words, you're going to configure the same things, but one of the differences here is configure the general purpose port pin that the data is coming in. Make sure that's an input, not an output. The LED on this end is still going to be an output. You're going to read the logic level of the input pin. Whenever you see it fall low, go low. Then, yeah, that's the start bit. So you're going to wait for that 1.5 time units. And then you're going to go and enter a loop that goes through and reads, samples that line using kind of that digital input capability. Kind of a digital read of that line, that input line. Same way you did in Lab 2. And you're going to delay each of the times and form that by reading it in, ORing it on, and then the next time in the loop, shift it over, put the next one on, shift the next one over, put the next one on. A couple words of caution here. The order that you do those things in the loop matters, because if you OR it on and then shift, when you're done, it's going to be shifted 1 too far. So you probably want to shift first and then OR, shift first and then OR. So at the end, you're going to have it the exact message in there without it being shifted 1 too far. And then after that, you're going to display the character that was received. Now, there is one other possibility, and that is if you get all zeros, in other words, the start bit was a 0, all the other bits were zeros, the stop bit was a 0, then that's what's called a break condition. That's what would happen if the line was disconnected. The digital input is low. You just get all zeros, the entire thing. So that's going to be a break condition. Now, if you get to the stop bit and you read it, and it was something other than the same as the idle, and something other than 1, but the rest of the bits weren't 0, then you need to have an if statement that does that, and that's going to be a frame error. So in other words, if you read the stop bit and it reads 0 in the stop bit's position, and not only does it read 0 in that position, but the data bits that you read were all 0, then that's a break error. But if I read the stop bit and it's 0, and the rest of the bits were not all 0, then that's a frame error, meaning something went wrong. The stop bit should have been 1 here, and it was 0. And we got other stuff before that that wasn't 0, so something went wrong. And it's called a framing error because what we'd expect at the stop bit period was not what we saw there. We should have been in the idle state, and it was something else at that point. Now, it's important to get the timing synchronized between the receiver and the transmitter. So you got to make sure if you change the rate on one end, on one program and recompile it, change it on the other one and recompile it. Because even though they're asynchronous, the timing between each of the bits matters. It has to be really close for this to work. Usually like plus or minus 10% in order for this to stay synchronized over that 10-bit period there. All right, so I want you to test the working system at 10 BPS. In other words, on the one end, you'll type let's say capital A, hit enter. On the other end, you'll see it. You'll see the LED flash on the other end, and it'll say capital A on the other end. And you should be able to then, once you've done that, type in like HELLO and hit enter, and you'll see on the other end, the receiving end, HELLO come through on the other end. So after you get it working at 10 bits per second, increase the rate to 120 bits per second, 1200 bits per second, and 2400 bits per second, and test that, make sure it works at those rates. If you do have issues with that sending at those higher rates, then there's probably something with your timing, or keep in mind you need to use the delay microseconds when we get up to these rates here rather than milliseconds. Okay, so that's what the lab is. Let me switch back to the presentation for just a second here. All right, so that's what the lab is. Relatively short lecture today, only about a half hour, and that's because I wanted to give you time to work on the lab, which you should have now. So if I were you, I would take advantage of that. So make sure your Lab 2 works. Make sure to work on Lab 3 during this period. Don't put it off because we're going to have more labs coming up. Next class, we're going to start talking about synchronous communication rather than asynchronous, which is what we're doing now. And get this one done because you have basically a week to get this done. So don't procrastinate and dawdle because you'll be late. And other than that, if you do that, then the labs are going to start backing up and you're going to get behind and you're going to get discouraged. So stay on top of it. If you have questions, let me know. If you need help, let me know. If you are having problems, let me know. Also remember, you can work with a partner on this one, but I would encourage you to not go outside your social group, or if you do and you meet somebody in a lab, wear a mask, kind of sit 6 feet apart. The Arduino cables are long enough that will allow you to wire it up and then not be near each other. So try to stay within your own social group just because there's still a global pandemic going on and 4,000 people a day are dying from that, so we don't need to spread it any farther or wider than we need to. And until next time, stay safe, wear a mask, wash your hands, and get to work on that lab. Make sure to submit that. Now, when you submit those, one word of advice here, since you're submitting the 2 different programs for Lab 2 and Lab 3, you have both the transmitter or sender and the receiver. Just make a zip file, drop both of the .ino files into that zip file. The INO files are the kind of the source code for those, and submit just the one zip file. And that will be good, and I'll unzip it and test it or look at the code, test it on my end, and grade it. Also, make sure at the top of each of those programs on both the sender and receiver to put a comment block. Since it's C and C++, you can use / for the comment block, or /* and put multiple lines in, */. Just like C and C++ comments. Make sure to put that in the top. And if you worked as a group, make sure to put both people's names in the code, your name and the person you worked with in that comment block as well. All right, so that's it. Everybody stay safe, and let me know if you have problems. Send me an email, give me a call, send me a text message, whatever. But if you're struggling, don't procrastinate. Let me know. I can certainly come down to the university and help you if you need that. But stay on top of it. That's it.